All right, so hi everyone. Thank you so much for coming to my talk, and also thanks to Brad and Ilias for inviting me. So what I'm going to talk about is roughly based on a collection of papers, and it's based on the ideas in there. So the motivation for this talk is really to state a key component of the MIP star equals RE argument in the language of group stability and operator algebras. Okay, and as you can probably tell, I am not an operator algebraist or a group stability theorist because I'm using PowerPoint. I'm a computer scientist, and and also if I say anything awkward during the talk, that doesn't sound right. It's me, not you. But I would also love to hear comments. But the key idea of what I'm going to talk about is that the stability of a group depends on the specific presentation that you're thinking about. And there's an important quantitative trade-off between the stability bounds you get and the complexity of the presentation. And I'll say more about what I mean here. And the main result that I'll talk about is that there is a presentation of the abelian group Z2 to the K that is both efficient and stable. So not only stable, but it also has this efficiency property. So to situate ourselves, I'll start off with Ulam's stability problem. And a version of it goes like this. So fix a group G. When are approximate representations of this group close to exact representations? And of course, the answer depends on the group you're thinking about and the notion of closeness. And so here we're, in general, we're going to focus on unitary representations of finite groups. Okay, and the notion of closeness is the normalized Hilbert-Schmidt norm. Let me be a little more precise. So let's first talk about what I mean by approximate representations. So let's say you have your finite group G, and you have a specific presentation with some generators S. The generators I'll call them Xi, and there's some relations between those generators. I'll call them Rj. Let f of S be the free group on the generators. Fix some distribution over the relations. So there's a finite number of relations. We're only talking about finitely presented groups here. So mu sub r is that distribution. And finally, u of d is the unitary group acting on CD. Okay, so let's define what an approximate representation of the group G with respect to this presentation. So we have this map phi. It's a homomorphism from the free group on the generators to the set of d-dimensional unitary matrices. And this homomorphism is an epsilon mu approximate representation with respect to this presentation if you sample a random relation from this distribution, that relation is approximately satisfied by this map phi, right? So how close this relation is under the map phi to the identity under the normalized Hilbert-Schmidt norm on average over a random relation is at most epsilon. And by normalized Hilbert-Schmidt norm, it's you take the trace of xx star, divide by the dimension, and take the square root. So hopefully the notion of approximate representation is clear. Okay, so let's say you have an approximate representation of your favorite group. How close is it to an exact representation? And that's this notion of stability. So some more definitions. Let's say you have a function delta of epsilon. We'll call it the modulus of stability. And you have another distribution, this time over the generators. So this is nu sub s. So we say that a group is delta mu nu stable with respect to this presentation if whenever you walk up with this approximate representation in the way that I just defined, there exists maybe some bigger dimension, some isometry mapping into this bigger dimension, and some exact representation pi of this group into u d prime, where this exact representation is close to your approximate representation on the generators on average. Okay. And how close, it's governed by this modulus of stability. So the modulus of stability is some function of epsilon, and you should think of as epsilon goes to 0, you want delta to go to 0. Right? So the closer and closer you are to an exact representation, so the smaller the epsilon gets, you want to be closer to an exact representation. Yeah. I think probably close to commuting. In terms of the no one since has done that. There's been in the last few years, I think people return to that setting. Yeah. Yeah. Any questions about this definition of stability?
Maybe you will comment on this later, but here you don't assume any bounds on D prime. It can be as big as you want.
As big as you want, yeah. So I guess in the people who work in this area, I think you usually call this flexible stability. So you don't have to necessarily preserve the dimension. You can go into bigger dimension to be close to an exact representation. Okay, so you can ask for what groups G, when is it stable? Maybe sometimes they're stable, maybe they're not. Okay, and just to keep things simple, and generally I won't talk about this distribution unless I need to. So just think in the back of your head, these distributions, there's just a uniform distribution over the relations and the generators. Okay, so people tend to talk about the stability of groups, but again, really the definition that I provided, it depends on the specific presentation you're talking about, because these error bounds hold on average over some distribution over the generators and relations.
Sorry, I didn't understand that. You're saying that this definition depends on the presentation and not on just the group?
Yes, like that is. Well, I'll say more on exactly this slide. So the definitions, at least you read them technically, there is some dependence on the choice of generators and the relations. Of course, many results in the literature on stability of groups, they don't depend on the presentation. Why is that? Well, you can make a generic argument saying that if a group G is delta stable for some with respect to one presentation, and delta is some function of epsilon, then if you change presentations, then you get a different delta prime. And what's the change? Well, you just multiply your epsilon by some constant. The constant depending on, somehow on the two presentations you're changing between. But the whole point of the talk is to really open this up. Like, what exactly is this dependence? Right? I mean, you could be hiding a lot here. And indeed, there's some really interesting things when you look at the exact dependence on of this constant on the different presentations you're considering. Okay. So really, we're just going to focus on one specific group, which is this abelian group Z2 to the K, and we're going to write all the operations multiplicatively. It'll be more convenient. So let's think about two different presentations of this group. So one is something I'll call the multiplication table presentation. So here, you're going to have a generator for every single element of the group. So there's a lot of generators. There's 2 to the K of them. And the relations that you're going to impose is that whenever C is equal to AB in the group, then you satisfy that with respect to the relations. So you just encode the multiplication table of the group into all your relations in this presentation. So you can see, if this is a pretty big presentation in terms of K, right? The number of generators and relations is 2 to the O of K. What if you wanted a more succinct presentation of this group? Here's something that I'll call the independent generator presentation. So now the number of generators is Y1 up to YK. And each of them you'll just impose sort of minimal relations on them. First, you'll impose an involution relation. Yi squared must be equal to the identity element. Okay? And yi and yj must commute for all I and j. This presentation generates the same group, but now it is much more succinct. It's much more compact. There's k-squared generators and relations. So, if you care about efficiency, and then you probably would prefer the second presentation, right? You don't have to write down as many things. How do they differ in terms of the stability of this group? So one can show that this multiplication table presentation enjoys very nice stability properties. So z2 to the k is O of epsilon stable with respect to the multiplication table presentation, meaning that if you have an approximate representation that's epsilon, it violates the relations in norm by epsilon on average, then it in fact is O of epsilon close to an exact representation. And you can prove this using a theorem of Gowers and Hatami from 2015. What about the independent generator presentation? So it's stable, right? And the constant in front of the epsilon depends on k linearly. And one way to prove this is to really just reduce to the Gowers-Hatami result, right? If you walk up with an approximate representation in terms of the independent generators presentation, you can build an approximate representation with respect to the multiplication table presentation, right? You just sort of multiply things and the error will accumulate. And how much do they accumulate? Well, it depends on the diameter of your group. And you sort of multiply things k times to get anywhere from one point in the group to the other. And that's why you get a linear blow up, linear and k blow up in the stability. Okay. And it turns out that this linear dependence on k is necessary for this presentation. So here you see they generate the same group, but you get different stability properties. Let's quickly see why this linear dependence on k is there. So I'll give you an approximate representation of z2 to the k with this independent generator presentation. So the generators are y1 up to yk. Phi of yi is going to be a self-adjoint unitary acting on the k-fold tensor product of C2. And I'll just describe it informally so we're not mired in notation, but we can think of operationally the unitary that yi gets mapped to. Think of it as acting on k bits, and it's just going to flip the ith bit. So if the bit in the ith position was 0, it flips it to 1. If it was 1, it flips to 0. Okay. This is an involution. It's unitary. It's nice. And we're only going to do this for bits 2 up to k. And for y1, we're going to map it to something else. It's going to be a bit flip, but it's going to be conditional on the second bit being 1. So this unitary, it's going to sort of look at the second bit, and if it's 0, it does nothing. And if it's 1, then it's going to flip the first bit. So this is an approximate representation. Why is it approximate? Well, you can see that y1 and y2 don't commute, right? It matters, right, whether you flip bit 2 or not. That will change whether bit 1 is flipped. But everything else commutes. They're involutions. So it's an approximate representation. Uniform measure, yeah. Yeah. Yeah, so, okay, so it's an approximate representation where epsilon is 1 over k squared. Why is that? Because only one of the relations, which is the commutation relation between y1 and y2, is violated. Everything else is satisfied. And there's k squared relations, right? You're checking every pair of commutation relations. Well, it's, but yeah. So the error is 0.
Just forgot the conditional approximate. Okay, it's the average.
So you basically, think of it, if you randomly sample a relation, how often are you going to see a violation? It's only with probability 1 over k squared. That's okay. And then the third point is, how far is this from an exact representation? Well, you can argue that it has to be at least 1 over k far in the L2 norm. And basically, an exact representation forces y1 and y2 to commute, but in the approximate one, they don't commute, and that's going to be 2 over k of the generators. And so what's the difference between these two quantities? It's a factor k. So that's the lower bound. Okay, so now you can see, the stability results do depend on the specific presentation you choose. And why do we care about this? Well, like I said, I'm a computer scientist, and in a lot of these computer science and combinatorics applications, we're really thinking about a sequence of groups, and so the size of the group is a growing parameter, and we really care about the dependence of the modulus of stability on the size of the group, and also the complexity of the presentation. By this, I mean, at least in this talk, I'm going to, complexity is just a stand-in for the number of generators plus the number of relations. So, to me, the gold standard, the thing that, would be great is if we have a sequence of groups where the group is delta of epsilon stable with respect to a presentation of the group, right? SK, RK, where the modulus of stability does not depend on K, right? It's just sort of, somehow these groups are just like universally stable no matter which group in the sequence you're taking. And also the complexity of the presentation scales as polylogarithmic in the size of the group. Let's say that there exists some measure that maybe it's nice, maybe it's computable, or something like that.
I don't know why you show in the number of generators, because if there are no relations at all, surely it's not complex. It surely doesn't, the complexity doesn't depend on the number of generators.
Oh, if there's no generator, you're saying every group is, the free group is always stable.
Right, but okay, well, the question is, you think its complexity ought to be 0?
Oh, if there are no relations, I see. Let's just say this is an upper bound on an intuitive notion of complexity. Yeah. Yeah. I mean, all the groups I'll think about here have some relations. Good. So this is the gold standard. This is what, as a computer scientist, I'd be shooting for. Okay, so this is the main results. That's really kind of an amalgamation of a bunch of results from some papers. So there exist some distributions, not uniform, mu r and nu s, and a presentation of z2 to the k, where this group is stable. And the complexity of this presentation is poly k, so it's polylogarithmic in the size of the group. And the modulus of stability doesn't quite meet the gold standard, but it's good enough for what we need. So it depends on some polynomial in epsilon, and it's multiplied by polylog in k. So remember, in this independent generators presentation, we paid a linear factor in k. Here, this is polylogarithmic in k. And at least for the applications we use it for, that's good enough. So that's the main result. So what's the key? What is this presentation? Well, it's constructed from error-correcting codes. So let me say what. Sorry?
You don't care how big the thing is?
It's some universal constant. I mean, you know, we can probably write it down. It's probably like 1 over 70,000. Huh? Yeah, small is yeah, smaller c is worse, because it. Yeah. So basically, it's like mu and nu are like convex combinations of uniform distributions that are nicely described, right? Like, I don't know. Yeah. I mean, they're not like crazy distributions. It's just that we perform lots of subtests. You know, we divide up the relations into different categories, and then you randomly select one from one category or another category, and each of these relations have different set sizes.
As a computer scientist, isn't it the fact that C was extremely tiny means that couldn't essentially the bound doesn't fit one no matter how small epsilon is? Wouldn't that happen?
I'm a theoretical computer scientist. Yeah. So, you know, we think about these theoretical computers. Yeah. Don't ask me to program this. I wouldn't know how. Okay, so let's talk about error correcting codes. You know, what are correcting codes? At a high level, they protect information from noise and corruption by adding redundancy. So I don't know, just to kind of like, you know, make a linguistic connection to stuff we've just seen, the information in an error correcting code is stable under perturbation. So maybe gives you some hint that this and stability are somewhat related. So formally, what's an error correcting code? An NKD code, or linear code, but we'll always talk about linear codes. It's a Z2 linear subspace of Z2 to the N. Okay. And the subspace has dimension K. And the important thing is that subspace has a nice property where if you take any two distinct points in the subspace and you look at their Hamming distance, it's at least D. Okay. So N is the block length. That's error correcting code terminology. So the number of bits that you're sending across your channel. K is the number of bits of the message that you originally wanted to send. And D is called the distance. So here's a picture of what an error correcting code looks like. You know, think of this gray box as the ambient space Z2 to the N. And then you have these points in this gray box. That's your subspace. That's your code. Each of these points are called code words. And the distance property is just saying that the minimum distance between any 2 points is D. So, you know, let's say on one end, I send one of these points across the channel, and maybe there's some noise or some perturbation, so that moves this point a little bit. But as long as the point is moved not too far, at most half the radius of this circle, then you can uniquely recover the original message that was sent. You can map it back to this point. So that's the distance property of a code. And you know, the way you encode is you take your message M, which is some vector in Z2 to the K, and you just map it to one of these points. And you know, there's a bunch of things that you would like to be large. One is you like the distance to be large because that governs how much noise and how much errors you can tolerate. Right? The bigger distance, the more noise you can handle. You would also like the rate, or K over N, to be as large as possible, because you know, the difference between N and K is basically how many more bits of redundancy you're adding. Okay, so you want K over N to be a large number. And the whole quest of, you know, coding theory is to try to design codes with as high a distance and as high a rate as possible. And there's a trade-off between them. They come in tension, right? So oh, and then one more thing. So there's another way of looking at an error correcting code. Any linear code, NKD code, can be specified as the kernel of some matrix. This matrix H is called the parity check matrix. So it has a number of columns, which is the block length, like the number of bits in your code word. And it has just a bunch of rows. And you can think of each of the rows as specifying constraints on what it means to be a valid code word. And finally, H is R local if each row has the most R non-zero entries. So, you know, I said the rows are constraints, And if it's R local, it means that the constraints only look at R bits of your code word at a time. Let's look at some examples just to get some intuition for these. So here's the dumbest error correcting code you can come up with, but one that we use all the time. It's called the repetition code. If you want to make sure your message is heard loud and clear, you just repeat your message. So this is a code of block length n, and it only encodes 1 bit. So k, the dimension is 1, so you only have 2 code words, right? The all 0 string and the all 1 string. And you've just taken your bit and just repeated it a bunch of times. It has an example of a parity check matrix for this code is this one. And intuitively, you can think of what it's doing is it's just checking that adjacent bits are equal, right? So if they're all equal, then that means you're a valid code word. Oh, and clearly the distance is n, so as long as the number of errors is at strictly less than half, the number of bit flips is less than n over 2, then you can uniquely recover the message that was sent. So that's a repetition code. Let's look at a fancier code. This is called the Hadamard code. I'll talk about what the code words are. So for every message m in z2 to the k, that's your message space, you're going to look at all linear, evaluations of all linear functions on this message. So you're going to take a k-bit message and blow it up to a 2 to the k-bit message. So there's a huge amount of redundancy here. And then each coordinate of this 2 to the k length code word is going to be the inner product between your original message and a distinct vector. Okay. So you're encoding all linear functions of your message. And it has great distance as distance 2 to the k over 2. Right? If you take any 2 code words, they're going to disagree in exactly half of their coordinates, which is the best possible. There's a nice parity check matrix for this. It's 3 local, and each row is just going to check the linear relation that if you look at, x sub a plus x sub b, then this is equal to x sub a plus b, where a and b are also elements of z2 to the k. You're just checking the natural linear relations for, to check whether you have a linear function. Okay, so has great distance, but the redundancy is quite a lot. What if you wanted to get a code with great distance but better rate, where you added less redundancy? So first, let me just say, we don't have to stick to Z2. We can talk about codes over larger alphabets, right? Your code words, each coordinate has a symbol from, some alphabet. Here, we'll think about alphabets that come from finite fields. Okay, but it's the same thing. They're just linear subspaces of the vector space fq to the n. And now, the distance between 2 code words is the number of non-zero coordinates of their difference. Okay, so now that we're in the world of larger alphabets, let's talk about something called the Reed-Muller code. And this is a very important error correcting code. It's used everywhere, like satellite communications, 5G, you name it. So people use this all the time. And there's a bunch of parameters. So there's a field size q, there's a degree s, and a dimension m. So it's there's some overloading here, but basically we think of our original message as something living in fq raised to the s plus 1 to the m. Okay, and basically you're going to take your message and interpret each coordinate of your message as a coefficient of a m-variate polynomial where each of the variables have degree at most s. Okay? And then you're just going to take this polynomial and evaluate it on every point in fq to the m. So if that was, that's kind of a mouthful, but just remember that the Reed-Muller code is really just evaluations of low degree polynomials. Before I talked about evaluations of linear functions. Now these are, they're not linear, but they're low degree. So, you work through the math and you get a code with this parameter. The important thing to note is the distance here is quite good. So this is something that's very close to 1. This is the block length. And so this is saying that if you take 2 code words of the Reed-Muller code and compare them, and they're distinct code words, they're going to differ in the vast majority of the positions, right? Which makes them very good for error correction. That's Reed-Muller.
When you're doing this, you're saying like you pick an S and then you pick the T to be very large.
There's different regimes. So S can also grow, but it grows as a slower function. And so you can, let's basically the point is this: you take the Reed-Muller code that I just described. You can also convert it back to a binary code, just because things are, just to keep things nice. At the end of the day, what do you get? You get a code with the following properties. The distance is very close to 1/2, okay, just like with the Hadamard code. But now the redundancy is much better. The block length is only some polynomial in k, not exponential like what it was before. You get this from the Reed-Muller code. Okay, so now we're going to use this code to get a presentation. How do you get presentations from codes? Well, we're going to get presentations of this specific group, z2 to the k. So let's say you walk up to me with an NKD code, and you chose a parity check matrix for it. Now, a code can have many different parity check matrices, but pick one, H. And we're going to define generators x1 up to xn. So there's a generator for every bit of your code word. And we're going to define the following relations. We're going to have the same involution relations that we had before. Xi squared is equal to identity. For every row of your parity check matrix, remember these were constraints on what it means to be a valid code word. We're going to drop that in and say that's a relation in this group. So you're going to have a relation for every row of your parity check matrix. And then finally, you're going to insist that every 2 generators commute. So those are the commutation relations. So notice that the difference between this and the independent generators presentation is that we have something coming from a parity check matrix. Okay, so this presentation has complexity at most n squared plus m. Right, n squared coming from the commutation relations and m coming from the parity check matrix. And it's not too hard to show that this also generates z2 to the k. And now we have a presentation with low complexity. We'd like to understand the stability of the group with respect to this presentation. So again, we'll take this binary Reed-Muller code where we've chosen the parameters, where block length is polynomial in k, distance is almost n over 2. The presentation has poly k complexity. And I'm just restating the main theorem, which is with respect to this presentation, we get this stability result. And maybe I'll say a few words about how this is proved towards the end of this talk. Okay. So so we've seen, you've chosen this code, has these nice properties. You can see where the block length and the k and the dimension of the code come into play. It manifests itself in the complexity of the presentation. You also had to choose a nice parity check matrix, right? The number of rows shouldn't be too large. But what about distance? Where does this d parameter come from? And I think the picture here is it's not totally clear. In this specific result that I mentioned, at least in the proof, you can see, the distance of this binary Reed-Muller code is very important. I mean, without it, the proof wouldn't work. But we don't have a good general picture of why it's, how it plays a role in the stability of the group. So But it seems like it's, if you want a good stability result, then you want to start with a code that has good distance. And just for some intuition, let's go back to this, this bad presentation, which is the independent generator one. It corresponds to the code that has, it's the trivial code where you add no redundancy. So the parity check matrix is just the zero matrix. There's no rows, right? So you had no relations from it. And the distance of this code is the worst possible. It has distance 1, right? Any two distinct code words differ in just 1 bit, at least. So here's a question that I think would be really nice to clarify. So if you construct presentations of z to the k from codes in this fashion, how does the stability of the group depend on the distance of the code? And one possibility, and I don't have a lot of general evidence for this, but this is just some intuition, is that you cannot get a modulus of stability that scales better than, you have to have some factor that depends on the ratio n over d. So in the Reed-Muller case, d was n over 2, so that's just a constant. But if d is, let's say, square root n or worse than that, then you're going to pay a factor that grows with n. So I think this would be a nice thing to clarify. Okay, and now this connects to something that George raised. So here's another well-studied question in stability, which is very similar. So it's raised by von Neumann, Halmos and Rosenthal and others. If you have matrices that almost commute, when are they close to exactly commuting matrices? There's a ton of literature on this. I think people here probably know much more about it than I do. And there's positive, negative answers. So there are cases when they are close, and other cases when they aren't close. So here's one result from 2010. This is by Glebsky. And this is a positive answer in the unitary case. So let's say you have two unitaries, U1 and U2, and the 2 norm of their commutator is at most epsilon. So they almost commute up to epsilon in the 2 norm. Then there exists unitaries V1 and V2 that exactly commute, and the distance between the U's and V's is at most epsilon to the power 1 over 9. So very nice. Here's an application of the stability of Z2 to the K to the many operator version of Glebsky's theorem. So now let's think about what if you had many unitaries. So you had unitaries U1 up to UK. And now let's impose some additional assumptions. So let's say they're self-adjoint. And let's assume that for all pairs UI and UJ, the 2 norm of their commutator is at most epsilon. Then a corollary of the KE stability of Z2 to the K, where you're talking about the independent generators presentation, is that there exists exactly commuting unitaries that are also self-adjoint, V1 up to VK, where the distance between the U's and the V's is now K times epsilon. It's just really another way of stating the stability result of Z2 to the K. And it makes sense, right? Because the independent generators presentation, you're just forcing all pairwise commutation relations. Yeah. Yeah, this is keeping the dimension the same. And what was the? Oh, I see. Right, you would need the non-flexible version. Yeah, that's true. Yeah, that's a good point. Yeah. Okay, so I think technically, based on what I had just said, these V1 up to VKs would have to live in a bigger dimension, possibly. And then you're saying that you're close up to applying an isometry. But I think it should also hold in the same dimension.
Maybe you just basically choose V1 and then go to orthogonal space and then choose the next two and so on. I mean, you're using
Mm.
self-adjoint because you want to use the theorem. But if you just
Right.
iterate Leibniz theorem k times,
Uh-huh.
you should take for some more components and go into bigger spaces.
Uh,
I'm guessing, but it just seems that may be a just one here.
you're saying that this question is trivial if you go to.
No, I'm not saying. I'm just saying
yeah.
that my guess would be that you don't need self-adjoint.
I see.
Because I guess you need self-adjoint because you're using a theorem.
Yeah,
But
that's
otherwise
right.
You can just use his theorem and then go to next space.
I see.
I
Yeah,
may
possibly.
be wrong.
Possibly, yeah. I have to think about that. Yeah. Okay, so nice, and yeah, so that's cool. I guess yeah. So remark is there's an adaptation of Glebsky proof where you also get the many operator version, but the error scale, you don't get k times epsilon. You get some, basically epsilon. In order to get something meaningful, epsilon has to be exponentially small in k. Okay.
There's also things from uniform law. This is the range.
Oh, the operator, yeah. That was stated for the operator.
Did you mention that?
The dimension, I'm not sure. Yeah. I think the dimension stays the same in Lin's theorem.
Okay.
Yeah.
Anyway, can you not deduce one from the? I guess you cannot deduce one from the other because the same norm comes from the hypothesis and the proof.
Right. Yeah.
But you might ask what the norms are supposed.
You mean the?
Like an LP norm.
Yeah. Right. So yeah, so and then we have this, okay, you say, well, we have this stability result for Z2 to the K, but with this fancier presentation coming from this error correcting code, does that imply some statement, some version of Glebsky's theorem? And I think it does. It's a little weird, but I think it's somewhat interesting. So the corollary is that you have self-adjoint unitaries, U1 up to UN, and that they approximately commute. But you also know something else, which is that they almost satisfy these relations. Okay, so it's not just approximate commutation in the hypothesis, but also you satisfy these relations that came from this parity check matrix. Okay, so I don't know, where does that come from? But that's the assumption. Then in fact, you can deduce the existence of close by commuting unitaries, and the closeness is a much better function of K and epsilon. Okay, yeah, maybe there also might be some D prime in there that might have omitted the bigger dimension. Okay, so that's this connection with this approximate commutation question that people studied. And now in the last part of the talk, I'll sort of go back to at least terrain that I'm much more familiar with, which is, why do computer scientists care about stability questions? And I claim that really they've cared about it for a very long time, but they just didn't know it was called stability. And but now we see there's tons of connections, which is, I think, very exciting. So a form of stability of at least finite abelian groups, like Z2 to the K, they're super well studied in a bunch of topics: locally testable codes, probabilistically checkable proofs, or PCPs, property testing, hardness of NP approximation problems. So I'll say a few words for what is the connection. So first, let me start with probabilistically checkable proofs, or PCPs. And if you haven't seen it before, I think it's a really wonderful thing to know that it exists. So it says that there's many versions, many ways of stating it, but one way of stating it is, let's say you gave me a mathematical proof of some statement, okay, and it's written in say ZFC or your favorite formal system, and it has some length L, right? You can efficiently convert this proof into another format. I'll call it enc of P, and the blow up in this new format is not too large. It's some polynomial in the length of the original proof. But now, if you want to check the correctness of the original proof, you can do so just by choosing a few random locations in the new encoded proof. And how few? Well, just a constant number, independent of the length of the proof. you look at, you choose like 10 symbols in this new encoded proof. You look at them, do they satisfy the required relations? If so, then you have high confidence that the original proof is a correct proof of the statement. Just to illustrate it, let's say some aliens came down to Earth and they said, here's a 20,000 page proof of the Riemann hypothesis. It's written in alienese and you don't know what's going on. You say, well, why don't you help us out and do this PCP encoding of your proof? And I will randomly select 3, 4, 5 symbols in your proof, and I can verify with high confidence whether you actually proved the Riemann hypothesis or settled it. So that's what PCBs do for you. And yeah, well, it could be pretty smart aliens. So PCBs are great. It's one of the wonderful results that complexity theory has proved in the 90s. Well, she thinks it's true. So what goes inside what is the magic sauce? And it's really a form of stability theorems. I mean, nowadays, yeah.
I'm a bit confused. So this is a property of the proof, or it's a property, it's like,
So it's an encoding. It's saying you can write your proof in such a way that makes me, the reviewer, the referee, makes my job much easier. I just need to.
you're saying it's always true for all proofs?
Yeah. So if your proof was correct, I will verify that's correct. If it was wrong, there was, the thing with proofs, as we know, there can be just a bug in one place, and that makes the whole thing fall apart. But you had to find that place. The nice thing about PCP encoding is that if there are bugs in your proof, it spreads it out, and so that you would find, the error with high probability. So even one mistake, yeah. So that's and why, how is this possible? And it really comes from a form of stability. And in the computer science literature, these are go to the name of locally testable codes. Okay, so error correcting codes make another appearance. So it's an additional property in error correcting code. So let's say you have an NKD code, has some parity check matrix. We'll say that it's R comma delta locally testable. If the parity check matrix is R local, right? Only think of R as a constant, like 10, right? You're only looking at 10 bits of your code word, where you walk up to me with any vector in Z2 to the n. So someone is claiming that W is an actual code word. Okay, just like someone is claiming they have a proof of the Riemann hypothesis. You say, well, I don't have time to look at the whole code word. I'm just going to sample 10 random bits according to the parity check matrix. And let's say you sample the 10 random bits and you see that the row is satisfied with high probability, or let's say another way, it's violated with probability only at most epsilon, right? So only an epsilon fraction of the rows are violated by this supposed code word W. That in fact tells you that W must be close, delta of epsilon close to an exact code word. Okay, so hopefully you can start to see the connections with stability theory. Okay, so a word approximately satisfies H, then it must be close to an exact code word. Yeah. It's just right. It wasn't an important error. Yeah. So. Oh, then you'll never detect an error. So the epsilon would be 0. So it'd be yeah. Right. So yeah. So that's why there's a statistical, like you choose randomly, and if you see that you haven't the fraction of errors is small, then you have high confidence that it was correct. So you're never 100% correct sure, but when are we ever sure? Okay. So. Yeah, local testability is a wonderful property, and it's highly non-trivial, right? It's not like you walk through the street, you run into an error correcting code. It's not likely to be locally testable. And in fact, you can make in a precise sense if most codes, right? If you sample a code at random, they're not locally testable. So it really requires work to create. But there's some nice examples. So this Hadamard code I described, it's locally testable. You only have to look at 3 random bits of a Hadamard code selected at random. I mean, according to this distribution XA plus XB equals XA plus B. And if those checks pass with high probability, you have high confidence that the thing was actually a Hadamard, close to a Hadamard code word. How do you prove this? Well, you use Fourier analysis over z2 to the n. It's not too long, it's pretty nice. But again, the main drawback of this code is, the redundancy is really large. Okay. What about the Reed-Muller code? Turns out that it is also locally testable, and it has those parameters, like the number of locations in the Reed-Muller code that you have to examine only depend on the degree of the polynomial that you were using to encode things. Okay. And there's been a ton of work on this starting from the 90s, and people keep on proving new local testability results for the Reed-Muller code and its variants. And it's much more difficult to prove the local testability of this. Okay. Basically the task is someone hands you like the evaluation table, some function that if you look at local pieces of it, it looks like a low degree polynomial, evaluations of low degree polynomial. Can you deduce that this thing was actually globally close to a single low degree polynomial? That's the hard part. And there's different ways of proving it. Maybe I'll mention that the original proof, and actually many of these proofs, you sort of have an inductive proof where you have local slices that look like low degree polynomials. You start pasting them together, and there's going to be errors along the way, but you have to fix them. And you argue that you keep on building a bigger and bigger thing that looks more and more like a global low degree polynomial. And the trouble is, how do you control the error? And that's really the magic. So that's a hand wavy, I don't know, just to give you a sense of what these proofs look like. But the local testability of this Reed-Muller code is the thing that unlocked all these amazing things like PCPs. Okay, so the connection with stability is not just, it's not just an analogy, it really is a formal thing. So this notion of group stability is actually a strictly stronger notion than local testability. So let's say you have a code with some parity check matrix and you construct this presentation according to the recipe I described. If your group is stable with respect to that presentation, then it in fact implies the local testability of the code you started with. And really, you can think of it as locally testable codes as you're talking about stability of one-dimensional representations. But now when we're thinking about group stability, where you're talking about unitary representations of any dimension, well, that requires more work. And the way we proved our result, we followed basically one of the first proofs of stability of the Reed-Muller code, this thing, Babai, Fortnau, Lund. It's their proof approach, but there's a lot more work involved to get it to work in this arbitrary dimensions. And the fact that things don't commute exactly provides gives you a lot of trouble. But yeah, that's what the proof kind of looks like. Okay, so let me wrap up. So like I said, the motivation for this talk is I just wanted to state like one of the core components of this MIP star equals RE argument in the language of group stability. And really, it's all about the presentation that you choose. Gives you better. You choose the right presentation, you get the good stability bounds. Here's some open questions. We got a nice presentation that's efficient and stable, but not with the stability that meets this gold standard I mentioned, right? So there's still some dependence of this modulus delta on K, and it'd be great to get rid of this dependence. Like I think the belief is that there doesn't need to be a dependence on K. So it'd be nice to get rid of that. Other questions, just understanding more this general connection between codes and group stability, like what is the role of the distance parameter in a code? Here we've all just talked about the group Z2 to the K, but what about other groups? And just more generally and more vaguely, right? Like there's in computer science, theoretical computer science, over the last few decades, we've studied an amazing number of really cool objects, error correcting codes, locally testable codes, expanded graphs, things of all this nature that are all intimately linked to one another. And can we use these objects to get interesting operator algebraic objects? I think the answer is yes. Okay, so really this is the last part. So here's some analogies between some of the things that we study in theoretical computer science and some of the stuff that appears in operator algebras. So I said that the Hadamard code is locally testable. I use Fourier analysis to prove this. The corresponding result in operator algebras is this Gowers-Atami theorem. So it gives a general stability result for all finite groups. And the way they prove that is they perform Fourier analysis, but now over non-abelian finite groups as well. In TCS, people studied this local testability of Reed-Muller for a long time, like I said, and the main result of this talk that I mentioned is the operator algebra version of that. And again, the proof technique is we're following sort of the same footsteps of the classical version. So this follows this Babai-Fortnow-Lund proof. And now you say, well, okay, local testable codes were useful in PCPs. And so similarly, the stability result that we obtained was a core component of MIP star equals RE. And really, MIP star equals RE is, you can think of it as like, it's PCPs on steroids. Okay. The reason a big reason why people wanted to create probabilistically checkable proofs, in addition, not just because they wanted to, shorten the refereeing time, but really it was to show that there are NP hard computational problems that are hard to approximate. And similarly, using MIP star equals RE, we get the existence of algebras that are hard to approximate. So I think the dictionary between these two columns is quite compelling, and I'm sure there's many more things to explore here. Let me just leave it at that. So thank you.